Okay, and welcome back to BME 2315. Today we'll be continuing our journey through root finding. One of the things that you'll find as we look at the last two topics is, first we used a closed approach to finding the root, where we bracket it. On the second topic with Newton-Raphson system, we had an open approach where we only needed one guess, and we found that could converge very rapidly to a given solution. However, at least so far, both of these approaches have been limited into finding the root of just one single equation. But if you look at realistic examples, there are often many systems that are coupled together that can make it very challenging to solve all of the roots simultaneously for a system like this. And so this is actually a mathematical model of the cell and the biochemical signaling that happens inside the cell to mediate the fight or flight response. Basically how hormones like adrenaline make the heart beat harder. And in order to reconstruct this mathematically, we had to write out all the equations for all the chemical equilibria that were involved, and then use root finding in order to solve for the free concentrations of given proteins. And so this is just to give you a view of how, when you work towards research level problems, the scale of the math becomes a lot bigger, and that's essentially why we need computation. So basically now we're going to look at how we can deal with systems of equations rather than just one equation. And so as an example, on the left we have two equations, x squared plus xy equals 10 and y plus 3xy squared equals 57. Okay, so those are in their original form, and we're going to want to transform them by grouping the terms all on one side, and so that we would say that hopefully each of these equations would be such that they can be all thrown on one side, and then we rename these functions f1 and f2 as you see here. Note we went to the same process when dealing with the calcium buffering equations before. So basically what we're going to be doing is we're going to be looking at areas where f of 1 and f of 2 both equal 0. And that will be the solution to where these surfaces touch. So let's take a look at that visually. So we have a zero plane here in gray, right here, and then in red is the x plus xy minus 10 surface, and then in blue here we have the y plus 3x squared xy squared minus 57 surface. And if you look very carefully, you can see that there's just one point right here at which they all intersect on the zero line. Sorry about that, some PowerPoint issues. We had one point at which they all intersected at the zero line, and so that would be the solution to our system, where both surfaces equal 0. Okay, so that's generally what we're going to be trying to do, and so now let's look at how we're going to do it using the math. So the first thing is that we already talked about the systems of equations, and so we need to know how to write those. So f of x, and it can be any number of equations like this. And another so let's kind of look at how that applies to this specific example. So for this example, the F matrix equals x squared plus xy minus 10 and y plus 3 xy squared minus 57. Okay, so that's f1, that was f2. Okay, so the next thing we need to do in addition to being able to access the functions is look at derivatives. Remember in Newton-Raphson method, we used the function over the function's derivative. And so we need an equivalent of the derivative for this multivariate space, and that's going to be called the Jacobian. And so in general, it's taking the derivative of the ith function with respect to the jth variable. And so what that looks like if you expand this out is the first position is given by df1, dx2. The last position is dfn, dxn. And in these corners, this is dfn, dx1, and df1, dxn. Okay, so basically you got multiple functions and multiple variables by which you're taking the derivative, and that's what creates this structured matrix. So that's a little abstract. So let's now apply that to take the Jacobian of our system F here that's on the left. So J equals, the first one is going to be df1, dx1. Okay, so we're looking at this and we're saying we're going to take the derivative of this term with respect to x. It's going to be 2x plus y. Okay, then we're going to do df1, dx2. Okay, so we're taking the derivative of all of this with respect to y, and we just get x, because only the center term can handle the derivative with respect to y. Then here we'll be taking the derivative of the second equation with respect to x1. Okay, and all you get left is 3y squared. And then finally taking the second term and taking it with respect to y. And so you get a 1 right here, and you get a 6y off of this term right here. 6xy. Okay, so we just took the Jacobian of the system right here. And so we'll be using that when we try to solve for the nonlinear systems of equations. Okay, so as you remember when we talked about Newton-Raphson method, the Newton-Raphson method came from rearranging Taylor series, and so the multivariate one also relates to Taylor series. So it's first helpful to talk about a multivariate Taylor series. So as you remember from the beginning of the class, we have that the next value of a function can be given by its current value plus some combinations of derivatives, as you see in these higher order terms. So this is written as a first order approximation. It turns out that you can also do multivariate Taylor series approximations, and the formula is basically the same, that the function at some x location at I plus 1 is given by the current plus the Jacobian times this distance. So basically, our simple derivative is being replaced by a Jacobian, but otherwise the form is basically the same. And because of that, that means that our Newton-Raphson formula is going to look very, very much the same. So this was the original Newton-Raphson formula that we talked about as being xi minus f over f prime. And in the same way, we have a similar structure that's x minus, and we can't divide by a matrix. Remember, J is a matrix. And so instead we're multiplying by its inverse. So we multiply by its inverse and then multiply that by f right here. So this gives us a multivariate version of the Newton-Raphson method. Remember, multivariate is important because we're solving for multiple equations at once. Okay, so let's now do an example where we solve for this, solve for the solution of these two equations, even though that they're multivariate. And so I've got a few things at the top to keep track of. One is the overall equation for Newton-Raphson method. Also, let's put down the initial points. And we'll just note for later that the true root is at 2, 3. Okay, and so you start by writing out what x0 is 1.5, 3.5, and we're going to need to know the Jacobian. You notice that this is the same equation that we just solved a little bit ago, so the Jacobian is still the same. So it's 2x plus y, 3y squared, x, and 1 plus 6 xy. Okay, and our F matrix is x squared plus xy minus 10, y plus 3xy squared minus 57. Okay, so now we have the pieces to put these pieces into the Newton-Raphson method for multivariate systems. So on iteration 1, you say x1 equals x0 minus, and so now remember we got the Jacobian, and then the Jacobian for this system, if you plug in, we're going to plug in into the Jacobian 1.5 and 3.5, and so you should be getting 6.5, 1.5, 36.75, and 32.5. Okay, remember from the equation that this is actually the inverse. And then we're multiplying that by f. Okay? And if we plug in 1.5, 3.5 into f, we should get negative 2.5 and 1.625. Okay. So the next thing we need to do is actually compute this inverse right here. So I'm just going to write it down right here. So if you can, in your calculator or using the determinant or the matrix inverse equations that we had before, either of those approaches would be fine for calculating what this inverse actually is, but I'm just writing down the result for sake of time. Okay, so this is the inverse of that matrix. And so if you multiply this times this, and you subtract that from 1.5, 3.5, then you should get the following result. 2.0360 and 2.8439. Okay. And one of the things that's nice about Newton-Raphson method is that it converges so quickly. So notice that the true percent error is not going to be very big because it's actually pretty darn close to 2 and 3 already. The true error on this is 4.4%. Oh, actually, sorry, let me back up and say that because these are vectors, we use a different formula for true error. And so the true error is the norm of x true minus our estimate divided by the norm of x true times 100, and that's what's equal to 4.4%. So the reason why we need to do that is that our answer is now a vector, and so we need a vector-based approach to calculate the error. Okay, so let's now, so this shows kind of step-by-step how to do this for the first iteration. And then on the second iteration, x2 is going to be given by, you're going to start off and you're going to be plugging in these numbers. Where before we had 1.5 and 3.5, here we'll have 2.036, 2.8439, okay, minus, and then you'll have a term right here, and you'll have the f term right here. And the final answer that you should get if you plug in all those numbers is 1.9987, 3.0023. So you can see that after 2 iterations, you get very close to the actual answer right here. And so again, the true error in this case which is the norm of x true minus x2 divided by the norm of x true times 100% and equals 0.07%. Okay, so it got down very, very close in just 2 iterations. Okay, so to sum up what we've been going through today, the Jacobian matrix is a way of capturing the first order partial derivatives of a vector valued function. And so it's a way of expanding into multiple dimensions here. We saw a multivariate Taylor series that has a form that's a lot like the single variate Taylor series, but uses the Jacobian matrix. And so that's one of the reasons why Jacobian matrices are important to know about. And finally, we found that the multivariate Newton-Raphson method allows us to solve not just single equations, but systems of equations, nonlinear systems of equations that you couldn't solve with either the single variate Newton-Raphson method, nor could you solve them with Gaussian elimination because these are nonlinear systems. So that's why these methods are important. And the basic idea is that it's using the Jacobian so that it can calculate all the partial derivatives that are needed. Hope that was helpful for you, and see you next time.